Have you ever wondered how your computer sorts data so quickly? In this video, we will explore one of the most popular sorting algorithms in computer science, quicksort. We will take a deep dive into how quicksort works, then we will look at the code, we will look at the complexity of quicksort, and finally, we will look at the advantages and disadvantages of quicksort. So, without any further ado, let's get started. Quicksort is a divide and conquer algorithm that works by selecting an element as a pivot and partitioning the other elements into two subarrays according to whether they are less than or greater than the pivot. The subarrays are then sorted recursively. The key process in quicksort is partitioning. The algorithm selects a pivot and partitions the array around it. The goal of partitioning is to place the pivot at its correct position in the sorted array and put all smaller elements to the left of the pivot and all greater elements to the right of the pivot. Partitioning is done recursively on each side of the pivot after the pivot is placed in its correct position, and this finally sorts the array. But how to pick a pivot? There are many different choices for picking pivots. You can always pick the first element as a pivot, or you can always pick the last element as a pivot, or pick a random element as pivot, or always pick the middle element as pivot. In this video, we will always pick the last element as a pivot. Now, let's look at the working of quicksort with an example. Before we understand quicksort, we need to understand how partitioning in quicksort works. Remember that quicksort sorts the array by recursively calling the partitioning on the subarrays. We have an array of 5 elements 10, 80, 30, 90 and 40. In this video, we always take the last element as the pivot. So 40 is our pivot. The partition algorithm keeps a pointer, let's name it I, which keeps track of the small element than pivot. The algorithm starts to compare all the elements of the array with the pivot. If the current element is less than the pivot, we swap the current element with the ith element and I is incremented. Remember, I was a pointer. If the current element is greater than the pivot, we just ignore and do nothing. Now, let's apply this to our example. Our pivot is 40. I starts at the first element. We start with the first element 10. 10 is smaller than pivot. We swap 10 with the ith element. Here 10 is the ith element. Swapping takes place but no visible changes. I is incremented. Now we compare 80 with the pivot. Clearly 80 is greater than the pivot 40. As per the rule, we ignore it. I remains as it is. Now we compare 30 with the pivot 40. 30 is smaller, so we swap 30 with the ith element 80. 80 and 30 are swapped with each other. I is incremented and it now points to 80. Now we compare 90 with the pivot and clearly 90 is greater, so no swapping. Finally, the pivot has to be arranged in its correct position. That's where the ith pointer really helps us. We just have to swap the pivot with, you guessed it, the ith element. Note that all the elements to the left of the 40 are less than the 40 and all the elements to the right of 40 are all greater than 40. This is how partition sort works. As you can say that the array is partially sorted. This is where quicksort comes into play. Now let's take our previous example again. As a first step, quicksort partitions the entire array, which results in elements 10, 30, 40, 90 and 80. Note that 40 was our pivot. Now quicksort applies partitioning on the left subarray, that is the elements less than the pivot 40, and applies partitioning on the right subarray, that is the elements greater than the pivot 40. When partitioning is applied to the left subarray, 30 is selected as the pivot. 10 is compared with the pivot 30. 10 is swapped with the ith element. Here 10 was the ith element, so no visible changes. I is incremented. Since there was only 2 elements, the iteration stops. The pivot 30 is swapped with the ith element. Again, I was the element 30 itself, so no visible changes. Note that the left subarray was already sorted, but the algorithm kept on processing. This is one of the drawbacks of quicksort. More about that later. When partitioning is applied to the right subarray, 90 is compared with the pivot 80. 90 is greater, so no swapping. I remains in its place. Now the pivot has to be brought to its place. So we swap the pivot element with the ith element. And yes, our array is sorted. Note that quicksort recursively applies partitioning on both the left and right subarray until the array has 2 elements. Quicksort never creates new array for sorting like merge sort. Instead, it sorts in place. This is how quicksort works under the hood. Before looking at the code, if you find any value in this video, hit that like button. For more content on algorithms, hit that subscribe button. I promise, you will not regret. Now, let's look at the code for quicksort. We have a basic structure of a C file. We have included the header file. We have implemented the print array function which prints the array. In the main function, we have declared an array to work with. N contains the size of the array. Then we print the array before sorting. We implement the quicksort which takes parameters array, the low and the high, which is low is the start of the array to be sorted and high is the end of the array to be sorted, that is the index of the element of the end of the array. Then we check if low is less than high, that is if the array contains more than one element, then we apply partitioning to the entire array. We recursively call the quicksort for the left subarray and recursively call the quicksort for the right subarray. Let's look at the partition algorithm. In the partitioning, the partition takes 3 parameters: array, the low, that is the start of the array, high, the end of the array. We implement pivot of that array. Then we have the ith pointer. We initiate the ith pointer to the low of the array, that is the starting element of the array. We run a for loop which runs from low of the array to the high, that is it traverses to the entire array until the pivot. In the for loop, we have a if condition which checks if the current element is less than the pivot. We swap the current element with the ith element and increment the ith point. After the for loop, we bring the pivot to its correct position, that is we swap the ith element with the pivot element. Then we return the position of the pivot in the array. This is the code for quicksort. Let's look at its output. As you can see, the array before sorting is 20, 1, 3, 12, 10, 0, 5. The array after sorting, that is after quicksort is applied, it forms 0, 1, 3, 5, 10, 12, 20. Yes, the array is sorted. The source code is in the description. The worst case complexity of quicksort is big O of n square, which occurs when the pivot at each step consistently results in an highly unbalanced position, or when the array is already sorted and when the pivot is already chosen as the largest or the smallest element. To overcome the worst case scenario, various techniques like choosing a good pivot by finding the median of 3 or using random pivot is used. Quicksort really shines in its average case complexity, that is big O of n log n, making it one of the fastest sorting algorithms. The advantages of quicksort is that it is a divide and conquer algorithm that makes it easier to solve problems. Quicksort is efficient on large dataset and it has a low overhead, as it only requires a small amount of memory to function. Some drawbacks of quicksort is that it has a worst case complexity of big O of n square, which occurs when the pivot is chosen poorly. Quicksort is not a good choice for small dataset, and it is not a stable sorting algorithm, that is, the relative order is not preserved in the sorted output. Finally, if you like video on algorithms, then consider subscribing. Congratulations on mastering quicksort. Signing out.